Look at chapter 8, enzyme kinetics. You have there the instructional objectives and then importance. Right. Chemical reactions are described using balance equation. So you are familiar with this equation. A plus B equals P plus Q. You have the reactants here, A and B, and the products, E and Q. Okay. And of course, the double arrow that you can see here, it means reversible. All right. Now, in physiological reactions, you may have a reaction that goes forward only. That means a one-way reaction towards the right when the products are removed. How are they removed? By further reactions in a metabolic pathway.
Oh, shit.
Oh, there you are. So the reversibility here is intrinsic property of all chemical reactions. You have A and B can form P and Q. Then P and Q can also become A and B. So whichever is, for example, if you have high concentration here of A and B, reaction will go this way, B plus Q. However, if this is high in concentration, the backward reactions can occur. So that's reversibility. But if this is removed, then you will have a reaction like this, where you only have a one-way reaction going forward. Okay? As long as the products are removed, they are removed by further chemical reactions going on in a metabolic pathway. Okay. Changes in free energy determine the direction and equilibrium state of chemical reaction. You are, of course, familiar with Gibbs free energy, no? Gibbs free energy change. Ili ni si Jano Gibbs, ha? So delta G, also called either free energy or Gibbs energy. Okay. So this delta GP is product. And this delta GS is substrate. Free energy of the substrate and free energy of the products. All right. The equation that you see here is a relationship between equilibrium constant, KEQ here, and delta G, standard free energy, is equals to negative RT, normal logarithm of your equilibrium constant. Don't worry about this. I'm not going to ask you this. No, I just want to show you the relationship. Huh? Okay. So here it is. So that's your delta G equals to negative RT normal logarithm times your normal logarithm of your equilibrium constant. So R is the gas constant. That's 1.98 calories, mole calories per mole, or 8.3 joules per mole. Okay. And T is the absolute temperature in Kelvin. Okay. Don't worry about this. I won't even ask you about this. Calculate for the equation. Okay. So we have here this reaction E plus RL. No? RL. Now that is not negative sign there. It means that R is attached to L and L is attached to R. It's equals to, you see this? The R has been transferred to E plus L. Okay? Now, I just want you to know about this transition state and what is this. So here it is, your transition state. Wait a minute. Okay. Now, before this R forms a part of E, like that one, there is what we call a transition state, where R is attached to L and R is attached to E. And it looks like this. And you notice it is dotted line. Oh. So that is what we call a partial bond. It is not a true bond. Now, once this is ruptured, the partial bond between R and L, then R forms a bond, a true bond with E. You get it? Example. You have here E, and then you have here this with a phosphate. So this is molecule A and molecule B. All right. In this center now, you will see that the phosphate is attached to E and it is also attached here. Look at that. You see that? And then this is cut off here and the phosphate now is attached to E. So this is the product P and that is your Q. Okay. That is what is meant by transition state. Oh, here again. Transition state and then breaking of this bond, you have now ER plus L. Okay, so that is what is happening now. All right. Delta GF, and what is F? Formation defines the activation energy. Okay, example to show before we go into that. So we'll have to talk about factors that affect reaction rate. we have this what we call kinetic theory, also called collision theory. All right. Now, there will be no reaction unless your molecules collide with each other. Now, if these molecules have a very low kinetic energy, so they become stagnant. Reaction is very slow if there is. All right. Now, always remember that the atoms and electrons are always vibrating. So it has a form of its own energy. It's always vibration. And since you are made up of atoms, you have a certain vibration. And that vibration is usually measured as a frequency. Now let's not go into physics anymore. So this you'll just have to remember that it requires collision. The molecules have to collide. Now if the molecules are not moving or very, very slow moving, reaction should be also very, very slow. Because you cannot have a reaction unless the molecules collide with each other. Okay, that's kinetic theory. Now, if you remember in your kindergarten chemistries, whenever you are going to hasten a reaction, you always heat it, di ba? Usually in a test tube, and you have a test tube holder, and you have it heated in a Bunsen flame, and then the reaction occurs very, very fast. Now, heating, temperature increases kinetic energy, and you are increasing the collision rate. So when they collide more often, more reaction is going to occur. You have seen that, di ba? In your previous chemistries. All right. So here it is, temperature. Raising the ambient temperature increases kinetic energy of molecules. So what is this illustration here? Have an idea what is this? All right. Here is your reaction with a low kinetic energy. Now, this bar here is an energy barrier, which means that if you cannot attain the energy to cross this barrier, no, there is no reaction. So you must have to increase the kinetic energy of your reactants, shown here now. Okay, the shaded portion is already, the kinetic energy is very high. So that's why it's getting in and passing through the energy barrier. So you have a high kinetic energy here already. So kinetic energy is increasing that way. Okay. All right. Another is reactant concentration. If you have a small number of molecules, naturally, reaction rate will be slower. It will be slow. So, increasing the reactants would naturally increase the rate of reaction. Diba? Like for example, now we are in this pandemic, we have it is required of us to be physically distancing from others. Now, what is the reason for that? The reason is, of course, that there is less chance of the virus jumping from one person to another because of the distance. So the lesser the people in a particular given area, the lesser are the chances of infection. The same way with the molecules. Fewer molecules, fewer collision, and fewer collision, fewer or low reaction rate. You get it? Now, KQ or the equilibrium constant is the ratio of rate constant. Never mind that. Now, this one is important. The kinetics of enzyme catalysis. Enzymes hasten chemical reaction by lowering activation energy barrier for a reaction. Okay, so look at this. This is your energy barrier. And if the kinetic energy here is just like that, your enzymes lowers the energy barrier. And so reaction can go that way. You get the idea? So the role of the enzyme is just to lower energy barrier. All right. There are so many ways by which the enzyme can lower the energy barrier. One is putting the molecules, together. See, they try to put the molecules as near as possible to each other so that a possible collision can occur rather than distancing itself. Do you get it? So let's go back to your enzymes. Enzymes lower activation energy barrier of the reaction. However, enzymes do not affect equilibrium constant. Although enzymes undergo transient modification during process of catalysis, they always emerge unchanged at the completion of the reaction. So there is no change in the enzyme. So the enzyme, the presence of the enzyme, therefore, has no effect for the delta G, standard delta G, for the overall reaction, which is a function solely of initial and final state of the reactants. And that is your reaction 25. Okay. All right. So multiple factors affecting rates of enzyme catalyzed reaction. Now this one with the presence of enzyme. Temperature here, temperature, just like in your previous chemistries, when you are going to increase the temperature, there is an increase of reaction. It is also true with enzyme catalyzed reaction, but there is what we call an optimum temperature. After that optimum temperature, meaning that the reaction is faster at the optimum temperature, but beyond that, the enzyme does not work anymore, or it works very, very slow until finally no reaction occurs. Why? Because enzymes in general are proteins. And proteins, when they are heated to a certain temperature, they become denaturized. They, meaning remove, nature, denaturize. So its original nature is changed. So that is what we call, there is what we call temperature coefficient. And what is this? Or Q10. For every 10-degree rise of temperature, there is a doubling of reaction. So from 0 degrees centigrade, you increase that to 10 degrees centigrade, the reaction there by the enzyme catalyzed reaction is doubled. Now, if you go further from 10 to 20 degrees centigrade, it is doubled also. But you should remember that our body has a normal temperature of around 37 degrees centigrade. Okay? Now, if you go beyond, then if you go beyond that, the enzymes does not work efficiently anymore because they tend to become denaturized and becomes another or nature or another protein. No? Okay. Those nurses, medtechs, they must have observed that a person with a high temperature above 39 degrees or 40 degrees, they tend to hallucinate. You are in the bed and having a high fever, then you tend to hallucinate. You will see your grandparents who had been dead 10 years ago and trying to, with their hand signal, they say, come with us. No? That's one form of hallucination. And usually it is like that they can see spirits or whatever. No? Okay. So that's the effect of high temperature. Now our temperature is peak at 37 degrees. So there is that reaction. Now what is the use of fever in our body? What's the use of fever in our body? Why do we have to have a high temperature when we are sick? First,
Immune
it tells
response.
us, okay, come on,
Immune
go ahead.
response against infections.
Okay, that's a response. Why should it respond that way?
Lymphocytes fight better when there's an increase in temperature or white blood cells.
Oh.
Reacts to changes.
Okay. What use of a high temperature? It tells you that you are sick. And that's the most important, knowing that you are sick. Diba? Now, there are diseases where there is no increase in temperature and you think you do not have any sickness at all. But with a high temperature, you know that you are sick. Okay. Another is to kill the organism or the infectious material that got into your body. you've been informed that the coronavirus is destroyed beyond 25 degrees centigrade. You see? Starting from 25 up to a higher temperature. And then why couldn't they survive at 37 degrees centigrade normal temperature, body temperature? Not only the coronavirus, but other viruses, influenza virus, common cold virus.
Because they are intracellular.
They get inside the cell. No, they are very clever. They cover itself and get inside. So it all depends on the viral load. If the viral load is not so much, then you may not have any signs and symptoms, and so you are asymptomatic. So you go around, you do not have the symptoms, but you are infectious. You can infect others. So that's the reason for put you in isolation or quarantine. Okay. So going back to our enzymes, temperature coefficient Q10, for every 10-degree rise of temperature, there is a doubling of reaction. All right. Hydrogen ion concentration. So the rate of almost all enzyme catalyzed reaction exhibit significant dependence on hydrogen ion concentration, meaning pH. So there is what we call optimum pH again. Kanina is optimum temperature. Or I have optimum pH. All right. You know that the enzymes in your stomach are very happy in that condition where it is acidic. A good example is your enzyme pepsin, an enzyme that acts on proteins. All right. Then you have your intestinal enzymes coming from the pancreas, and even the intestinal walls can produce enzymes. Now, the intestine is alkaline in nature. So by the time the pepsin from the stomach goes into the small intestine, the pepsin does not work anymore because the environment is not favorable for its activity. They are very, very active at low pH or acidic medium. However, other enzymes in the small intestine works well at a very high pH, an alkaline pH. And they do not also work well when they are transferred to an environment that the pH is low, being acidic environment. All right. So temperature, hydrogen ion concentration. Now, assay of enzyme catalyzed reaction measures the initial velocity or the initial rate condition. Okay, initial velocity or VI. of the reaction dose is essentially that the rate of the forward reaction, no? All right, I will explain it this way. You see this curve is sigmoidal curve. Oh no, it's not a sigmoidal curve. Hyperbolic curve. Okay. Down below here, you have substrate level or level of substrate acted upon by enzymes. So starting from 0, increasing towards the right. Now here, going up is velocity. Okay, from 0 up to maximum velocity. Now if you look at this curve, this one is seemingly straight. And then it starts to curve right away like that. No? Okay. Now you have 3 points here. A, B, and C. Okay. From 0 velocity to maximum velocity. 1/2 of this from here to there is what we call 1/2 velocity or 1/2 Vmax. 1/2 Vmax. All right. So let's look at this. Starting from 0, you have an enzyme. You add the substrate from 0, increasing it, and up to where you have your maximum velocity of the enzyme. All right. Now, you'll notice that this is somewhere here is your 1/2 of Vmax. Okay, increasing your substrate to a point B where you have 1/2 Vmax. And then you drop a perpendicular line to the substrate. This is the amount of substrate in here that brings about 1/2 maximal velocity. And that is what is called Km. M here does not stand for Monsanto. It's Michaelis. No, Michaelis constant. All right. So, what is Km? What is Km? Amount of
Response.
okay, amount of substrate. Yes, that brings about 1/2 maximal velocity. Very good. Okay, and that is Km. Okay, there you are. So that is what is meant by Km. And you know now what is Vmax, maximum velocity. All right. So Km means amount of substrate brings about 1/2 maximal velocity. Okay. So this is it. In the cell or whichever area of the body, you have a fixed amount of enzymes. The enzymes here are colored light brown, or what do you call this? No? And then you have substrate here. Looks like earphones. No? Okay. At point A, there's few substrate. So only one enzyme has a complex with the substrate. The complex between the enzyme and the substrate is known as ES complex, enzyme substrate complex. Okay? So all the other enzymes are still empty. It's area where the enzyme, where the substrate are supposed to bind. Okay? In here, compared to A, you have more substrate. Did you notice that? You have more substrate. As a result, because of collision, you have more now enzymes that are bound to this substrate. No? This 1, 2, 3, you have the enzymes fully bound to your substrate. This one is half bound. This one is half bound. That one is half bound. Okay? You notice that? That's point B. Which means the graph that we show you, what is point B? What is point B? Okay. Brings about half maximal velocity. All right. There you are. Now at point C, there's plenty. No? There's plenty. And all of the enzymes are bound. They are all AS complex. God bless. So you have so much of substrate that all of the enzymes are bound to it. AS complex. Okay. This is point C. And where is point C here? There you are. Maximal velocity. No? All right. To understand this, no amount of substrate can increase this anymore. Why? Because your enzymes are limited only. However, if you pour enzymes here, reaction would be further or would be increased. But, you know, the amount of enzyme in a cell is just limited. Because this enzyme, once it is going to do its reaction, it releases the product and that becomes empty again. That becomes empty. And once it is empty, then there's still plenty of substrate, then it binds again. Then another substrate binds. So if this one is completed in its reaction, it is released, then another substrate comes in. So that rate of reaction is already maximal and cannot go further by adding more substrate. Did you get it? All right. Now, usually to evaluate this, you know, it's very hard to evaluate when your line is curved. Diba? You have learned this somewhere, that you cannot evaluate when it is curved. So the way to evaluate this, you need to have a straight line like that. So how are we going to convert this? Two bright guys came up with what we call a Michaelis-Menten equation. By the way, Michaelis is a lady biochemist. Her name is, oh no, I'm sorry. It's not a lady. He's a male biochemist, but his name is a lady's name, Leonor. 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 Michaelis. Diba? Then Menten is a physician or a doctor. And before she became a physician, she was a mathematician. So you have a mathematician and a biochemist here. Michaelis-Menten. She's a female. And her name is, first name is Maud, M-A-U-D. But her second name, not her family name, is Leonora. So how come these two, Leonor and Leonora, just come together in the laboratory? So Maud, Leonora, Menten. And they have created this, the Michaelis-Menten equation. All right. Michaelis-Menten equation is being, you see, first, okay, let's try to, what you call this, evaluate this, no? V is equal, initial velocity is equal to maximum velocity times the concentration of the substrate all over Km plus the concentration of the substrate. That is Michaelis-Menten equation. All right. So let's try to look at this. When S, substrate concentration, is much less than Km, if S is less than Km, what is Km again?
Amount of substrate brings about half velocity.
Okay, the amount of substrate. So if the amount of substrate S is less than the Km, so you just drop this and just write Km. So here it becomes Vmax S over Km at this point A. Okay, now if, so it is initial velocity equals to Vmax times substrate concentration over Km. Now, this is a constant. This is a constant. A constant divided by a constant is equals to Allah, kalimut. A constant divided by a constant is a constant. So that's why initial velocity is the amount of substrate. And we know that this amount of substrate is less than Km. Okay, let's look at the graph again. This is point A. Where is Km? Here. Now, if you drop a line here, that's very lower than Km. So, initial velocity is equal to the substrate. You get it? This is almost a straight line. Diba? Okay. All right, that is when S is less than Km. Now let's go to B, point B. So when S is much greater than Km, no, at point C, where is point C? Maximum?
Maximum velocity.
Okay. So it's very much higher than Km, right? All right. So initial velocity is equals to Vmax times concentration of S all over Km plus your concentration of S. Okay. Now, since the substrate is very much higher than Km, Km is what? Km is removed. Oh, negligible. So we put only S. So initial velocity is equal to Vmax times S all over S. Right? And S is equals to S. So you cancel this. So initial velocity is equal to
Maximum.
Vmax. Maximum velocity, right? Okay, look at this. Let's go back again. So you understand. When substrate is very much higher than Km at point C, okay, so you drop Km. So initial velocity would be equal to Vmax. Did you get that? All right. So point C, let's look at point B. When S equals Km, so when the substrate is equal to Km at point B, so here we are. Initial velocity, the original Michaelis-Menten equation, and since Km is equals to S, then that's just 2S, correct? Yes or no? Yes. Okay. So now you cancel this S here and this S. So what do we have? Vmax over 2. Wow, 1/2 Vmax or half maximal velocity. So ang Michaelis-Menten equation is valid. Okay? Now, a linear form of Michaelis-Menten equation is used to determine Km and Vmax. So as we said, a curve that is hyperbolic, you cannot evaluate it, no? Or you cannot have numerical value there. So what they did to the Michaelis-Menten equation, starting from here, they invert the equation. 1 over V, so they put this up and this one down. And we have Km plus S over Vmax times S. Then the factor both sides. Okay. And the factor this, and we have Km over Vmax times S plus S over Vmax times S. Okay, so 1 over V, simplify it, and Km over Vmax, because this cancels itself. That's why like that, no? It's cancelled because they are all constants. Constant divided by constant is a constant. So that is 1 over S. Okay, and then this is cancels itself. So that will be 1 over Vmax. Now, going back to your mathematics, what does this remind you of? This equation, what does this remind you of? It is
Algebra.
zero. It is zero. The equation of a straight line is y. That's y. That's x. And that is b. No? Y is equals to ax plus b is a straight line. It's a straight line. So a plot of 1 over v as y as a function of 1 over s as x, therefore it gives a straight line whose y-intercept is 1 over v max. And that is what we call the Line-Weaver-Burke plot. So this is Vmax. Yeah, 1 over Vmax. That is your intercept, line intercept. The slope is Km over Vmax. Okay. Now, if we have a value here, no, if this point is 0.5, and that is 1, and that is 1.5 here, and you have 2 here. Okay? So if this is 0.5, how much is Vmax? Ala, algebra, balikan, algebra. Oh, very good. So, how did you get 2? Huh? 1 divided by 0.5.
5.
Diba? Because that's 0.5. 1 divided by 0.5 is equals to 2. Correct? Huh? Oh, sayon ra kayo, no? So if you have a value here of 0.5, then the Vmax is 2. Okay. Hale equation. I remember one of my student before, maybe about 2 to 3 years ago, when I remember. He wrote HELL, and it says Hale equation. No? Describes the behavior of enzymes that exhibit cooperative binding of substrate. No? It's not stretch our mind here. Let's forget that. Now here is very important. Competitive from competitive inhibition. Now, what do you mean by that? You have inhibitors for enzymes, and we have what we call competitive inhibitors and non-competitive inhibitors. Now, both of these inhibitors are used in pharmacology, no? Producing compounds that are competitive inhibitors or non-competitive inhibitors. So, what do we mean by competitive inhibitors is that they are inhibitors to a chemical reaction catalyzed by enzyme by binding to the binding site of the substrate. So the natural substrate of that enzyme, this competitive inhibitor competes for the binding. A very good example of this is allopurinol. Anybody who has gout? Anybody who has gout? Your parents have gout? You know what is gout? Huh?
Yes lang.
Oh, very high uric acid.
Uric acid.
Oh, uric acid. That's a normal compound that is produced by the body, uric acid. No? But this uric acid, they tend to deposit in the your joints. And these uric acid crystals are spiky. They're spikes. And so you can just imagine in between your joints, you have spiky materials there. So every time you move, there is always pain. Diba? Now, this uric acid is a result of increased degradation of xanthines. All right. Now, the drug allopurinol resembles the uric acid. Oh, how this? Yes, the xanthines. I'm sorry, xanthines. And so they are going to bind to the binding site of the enzyme that acts on xanthines to become uric acid. And since it is not its natural substrate for that particular enzyme, the enzyme cannot do anything, or there is no product that will be formed. So that allopurinol will just stick to the enzyme. And no catalysis will occur. So it inhibited the enzyme that converts xanthines to uric acid. So that's the advantage of using allopurinol, a competitive inhibitor, which binds to the catalytic site or to the binding site of the xanthine to the enzyme that converts it into uric acid. Okay. Now, what about non-competitive inhibition. Non-competitive inhibition, as the word non-competitive, it does not compete for the binding site of the substrate. They bind somewhere else on the enzyme, or they call it allosteric. Allosteric meaning other site or other place. So other place other than the catalytic site. So these molecules bind to that particular portion, but in doing so, it changes the enzyme so that the substrate could not bind anymore to the binding site because there is a change in the enzyme. That is what you call your non-competitive inhibition. Okay. So let's look at this. Oh, there you are. Competitive inhibitors resemble substrate. And we see here, succinic acid is the substrate of succinate dehydrogenase, and its inhibitor is malonate. Now it looks like succinic acid. Look at this. But it is only 3 carbons. We have shown you earlier, succinic acid has 4 carbons. It has a carboxyl group here. It has a carboxyl group here. But there are 2 of this. Okay. So malonic acid is the competitive inhibitor of your succinate dehydrogenase. From the word dehydrogenase, removes hydrogen. Oh, there you are. Okay, here is your succinic acid. Carbon, 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 carbon. It removes these 2 hydrogens from this carbon and this carbon. There you are, and becomes fumarate. And you cannot do that with malonate because malonate does not have this carbon and its hydrogen. What it has would be only this carbon, then this carbon, and this carbon. 3 only. Okay. In effect, competitive inhibitor acts by decreasing the number of free enzyme molecules available to bind substrate to form AS. Why? Because the competitive inhibitor is bound there perpetually with the enzyme because no products can be formed. Because once a product is formed, the product is removed. So how do we try to, if a person like that, no, he has taken up malonate, so how can we, as a way of affecting the or trying to stop the inhibition, or how can you remedy the situation? That's one. So how can you, Does that mean that you need to have exogenous succinate dehydrogenase to be injected to the person? That's one way, but is it possible? Okay, the way they do this in the hospital is they are going to flood the patient with so much of succinic acid, the succinate. So you will have more of the substrate than the inhibitor. And chances that you will have more binding with the succinate rather than with malonate. Increasing the S decreases the concentration of EI, meaning enzyme and inhibitor complex, and raises the reaction velocity. So you have to increase the S, or the natural substrate of that particular enzyme. Double reciprocal plots. What do you mean by that, double reciprocal plot? It's the line waiver. Remember the line waiver? Okay. Now here we are. This is the line waiver Burke plot, or the double reciprocal. Now look at this. That's the same. No, the straight line. The green one here is there is no inhibitor. Okay. Once it enters here, is you have your Vmax. Okay. Now, the presence of inhibitor, it does not affect the Vmax, but what does it affect? Look at it. What is that arrow being pointed? There. Oh, that's the KM. Okay. Which has the higher KM? The one in red or the one in green?
Red.
The red. No?
Red.
That's a minus 1 over KM. This is 0. Towards the left is negative. Towards the right is positive. Diba? Huh? This is 0. So, the nearer to 0, the higher is, no? The higher, okay. The nearer to 0, there, no? And then no inhibitor with the higher, or the KM, but that's negative. Diba? So meaning, with inhibitor, you need to have a very high Km to offset this inhibition. That's negative 1 over Km. This one is also negative. But is that you have the correct Km here because there's no inhibitor. You need to have a higher substrate when with an inhibitor. The Vmax is not affected. It's the same. With an inhibitor, the Vmax is still the same. Now, this is opposite. A non-competitive inhibitor lowers the Vmax, but does not affect the Km. The Km is still the same because the inhibitor doesn't bind to the binding site of the substrate. It binds somewhere else. So the Km is not affected. There you are. Km is the same, but you have different Vmax. Okay. And then that is the Vmax. With an inhibitor. 1 over Vmax, and also 1 over Vmax means you have a higher maximum velocity than compared to that one. 1 over Vmax, that one is also 1 over Vmax. Okay? So just remember that a non-competitive inhibitor does not affect the Km, but it affects the Vmax. The competitive inhibitor does not affect the Vmax, but it affects the Km. All right. So what is this IC50? Numeric value of IC50, that is half 50, that's about 50% inhibitory potency. The IC50. Okay, tightly bound inhibitors. There are inhibitors that tightly bound to the enzyme. That the concentration of inhibitor required to measure Ki falls below the concentration of the enzyme typically present in an assay. So these are tightly bound inhibitors. There's another type, irreversible inhibitors or poison enzymes. The one that we had here, tightly bound, but it does not mean that it cannot be released. While this one, irreversible, meaning once it binds to the enzyme, patay ng enzyme. It will not dissociate. This type of inhibitors blocks the function of the catalytical essential residue. What do you mean by residue? The amino acids that is found already in the polypeptide chain. Now, usually, amino acids that participate in the catalysis are the hydroxylated amino acid with OH, especially serine, threonine, yes, and tyrosine. But most common is your serine and OH there. So much so that much of the enzyme for protein, we call them serine proteases. Proteases, protein enzyme that acts on protein. Proteases, serine proteases. Another is cysteine. Cysteine, you almost always find cysteine in the catalytic site of enzymes because of its SH group or thiol group. Okay. Now, knowing this, and of course, enzymes that has positive or negative charges. So that means acidic and the basic amino acids. They contribute to the catalysis. So if you block this activity of this particular enzyme, no, this group of inhibitors are what we call mechanism-based inhibitors. They block the function of a catalytically essential amino acid residue. Yeah? So it is in the catalytic site itself that they destroy the activity of this particular amino acid residue found in the catalytic site. Okay. All right. This is your ping pong. Usually this ping pong is when you have a portion of amino acids that has to be transferred. Like the amino group. Let's say amino group of aspartic acid is transferred to a what you call carbon skeleton of the amino acid. When you say carbon skeleton of the amino acid is an amino acid minus the amino group. Like for example, glutamic acid, if you remove the amino group there of glutamic acid, what you have the carbon skeleton known as alpha ketoglutarate acid or alpha ketoglutarate. Okay, so all right, if you have alpha ketoglutarate and you want to make that into glutamic acid again, you need to have an amino group. And usually amino group from aspartic acid is transferred to alpha ketoglutarate. And alpha ketoglutarate becomes glutamic acid. Okay. So this is just a work of transferases enzymes. What is the class of transferases? You have class 1, class 2, class 3, up to class 6.
Class 2.
Class 2. Okay, good. So that is what is meant by transferring one amino group to another, and then your aspartic acid minus the amino group, no, becomes a carbon skeleton, and that can be become aspartic acid again by adding an amino group. So it's just in a, like when you're playing ping pong, no, the ping pong ball from one player to another. It just goes to one player, then back to the other player, and next, and next, and next. So that's your ping pong reaction. Okay. Knowledge of enzyme kinetics, mechanism, and inhibition aids in drug development. Many drugs act as enzyme inhibitors. I give you already one good example, and that is allopurinol for the treatment of gouty arthritis. So the goal of pharmacology is to identify agents that can destroy or impair the growth, invasiveness, or development of invading pathogens. So we come up with antibiotics or stimulate the indigenous defense mechanism, and that is to boost our immune system. In this time of crisis, we do not have a drug or a vaccine for this coronavirus, so we are just relying on our immune system. The immune system should be boosted. And there are, we have already vitamin C that can boost your immune system. Vitamin D3, that is the sunshine vitamin. So do not be afraid to go into the sunshine, especially during this time. Get your vitamin D3 direct from the sunlight. And then you have zinc. Zinc. It's quite important. All right, the third one here is halt or impede aberrant molecular process triggered by genetic, environmental, or biologic stimuli with minimal perturbation of the host normal cellular functions. Okay, so when you get genetic or environmental, whatever, no, comes to mind is cancer. You have your cancer drugs there. And so you have drugs that would inhibit the proliferation of the cancer cells. And also a drug that prevents the proliferation of virus. Because this virus is just like a parasite. They invade a normal cell and take over the mechanism of the organelles of the cell to produce their needed proteins so that they can multiply. So they are using the mechanism of the cells, our normal cells. So if you can stop this, then you can stop the corona. All right. Most drugs are metabolized in vivo. So what do you mean by that?
Inside.
Now, enzymes destroys, no? Sometimes the destruction of the drugs is faster than how it works in your body. So, for example, penicillin and other beta-lactam antibiotics block cell wall synthesis in bacteria by inactivating the enzyme alanine carboxypeptidase. And then the bacteria itself produces beta-lactamases that acts on the enzyme. No, that acts on the enzyme that destroys the bacteria. So they have weapons of their own. And so that particular antibiotic now becomes rendered useless. Diba? It cannot do its work because the bacteria has already produced. Its weapon against that enzyme. You see? And so, what do we do? Because the bacteria produce already a beta-lactamase, which you destroy a beta-lactam antibiotic, then we have to have an inhibitor that acts on the beta-lactamase of the bacteria. Okay. Let's break for 10 minutes so you can empty your bladder.